to explain hypothesis testing to you by way of an example. So let me set up a scenario and go through an example with you. So let's suppose that you work for a company that manufactures bottles of perfume, and you're the quality control inspector, and your job is to check the volume of the bottles coming off the production line. And these are 2-ounce bottles of perfume, and so on average, all of the bottles in your production are going to have 2 ounces of perfume. Okay, so that sets up our null hypothesis that the mean volume of perfume in the bottles, of all the bottles, is going to be 2 ounces. Now, your company tells you that for your test purposes, your alpha value is going to be 10%. Well, what does that mean? That says if the volume of perfume in the bottles gets to be too great, then you need to stop production and perhaps recalibrate some equipment to get it back down to 2 ounces. And your job is to make the determination of when that happens based on this alpha value of 10%. Okay, so what you're looking at is an interactive worksheet showing a normal distribution curve, and that's in blue. Okay, and the alpha value of 10% is the red shaded region here in the right tail. And basically the hypothesis test consists of taking a sample off the production line, computing a sample mean for your sample, and that would be the basically measuring the volume in each bottle in your sample and computing a mean volume for that sample. And then from that mean volume of your sample, you're going to compute a test statistic or a test value. And in this case, I'm going to denote it as Z0. And then you're going to look at your normal distribution curve and you're going to see where that test statistic falls. Does it fall in the area to the left of the red shaded region, which would be the non-critical region, or does it fall into the red shaded region? Now in the non-critical region, if your test statistic is here, then that says, then your decision is, for your test, do not reject the null hypothesis. That there is some random variation in the volume of perfume going into the bottles, but it's not so much that we need to be concerned that there's an overfilling going on. Now, if your test statistic falls into the red shaded region, then that's an indication that, hang on, there's too much perfume going in the bottles. We need to stop and recalibrate or do something that we're going to lose production time and might be costly. And as I said, your company specified that the decision point for that is going to be based on an alpha value of 10%. Okay, so with in a right tail test, with an alpha value of 10%, that gives you a critical value of 1.28, and that's indicated by the red vertical line, and it's denoted Z alpha here on the horizontal axis. So now one day you go and you collect your random sample and you measure the volume in each bottle in your sample and you compute the mean volume, and then you compute the test statistic, and let's say you get a value of Z naught equal to 1. And on this chart, 1 is denoted by the green vertical line and the Z naught here on the horizontal axis. Now you can see this, the green vertical line falls to the left of the critical value. So it falls into this non-critical region under the normal distribution curve. And our decision that we can make based on that is that we do not reject the null hypothesis, that while there's some variation in the mean volume in the perfume bottles, it's not significant enough to warrant stopping the production line and recalibrating equipment or anything like that. Now, let's suppose one day you take a sample and you compute the mean volume and you get a test statistic based on that mean of 1.6. Now you can see what happened when I used the slider to change the test statistic value to 1.6. The green vertical line moved to the right of the critical value and that put the test statistic into this red shaded region. And this, as I said, is the critical region. This is the region where a flag is raised and you're going to say, well, hang on, it looks like there's too much perfume going into the bottles and we need to stop production and perhaps do something to get it back to where we expect it to be, which is around 2 ounces. Because this indicates to us that it's different enough from the mean of 2 ounces that there must be something wrong beyond simple random variation in the amount that's filled. So that is basically what a hypothesis test is about. And what I just demonstrated is a hypothesis test using the critical value. And what I did was to compare the location of the test statistic, which we got from our sample, to the critical value, which we got from alpha. Okay, so that's a critical value method of doing a hypothesis test. So you take your sample, you compute your test statistic, and you see, is it to the left or smaller than the critical value, in which case I'm in the non-critical region, or is it greater than the critical value, which puts it in the critical region, in which case my decision is to reject the null hypothesis. Now the other way to do a hypothesis test is to compare the p-value to alpha. And on this curve, the p-value is the green shaded region to the right of the test statistic extending into the right tail. And that is the area under the curve. So when the test statistic is 1, the p-value is 0.1587 or about 16%. So this green shaded region is about 16% of the normal distribution curve. Now we compare that to alpha, 10%, which is the red shaded region. And you can see that the green shaded region is greater than the red shaded region, and that's an indication that we are in the non-critical region and our decision is to not reject the null hypothesis. Basically everything's okay. Now if we had gotten a test statistic of 1.6 and computed a p-value based on that of 0.0548 or about 5.5%, you can see on the graph that now our green shaded region is smaller than our red shaded region. Okay, so that's comparing 5.5% to 10%, and you can see that the p-value is smaller. When that happens, our decision is to reject the null hypothesis. Basically, it's saying the probability of getting a result of a test statistic of 1.6 or more extreme is 5.5%. And that probability is so small as to indicate that there's something beyond random variation causing this test statistic to be so far away from the mean value. Okay, so that's kind of a way to understand what the p-value represents. It's a probability associated with the test statistic, and when that probability is so small, it's small enough that it's significant it's unusually a significantly unusual result, that there must be something wrong, as opposed to just random variation in the volume of perfume going into the bottles. So that's a p-value hypothesis test where you're comparing the area or the probability to the alpha value directly. So those are the two ways to do a hypothesis test. Now in this worksheet, this is at my website purplemonkeymath.com, so you can come here and you can play with these values to see how the comparison works and how you get the decision based on comparing either the test statistic and the critical value or the p-value and alpha. So you can adjust alpha. Let's say we move alpha to 5%. You can see it moves the decision point to the right, and then with a test statistic of 1.4, we are in the non-critical region. If we move the test statistic to 1.8 or 1.9, that puts us into the critical region, and our decision changes to reject the null hypothesis. So as I said, you can come here and kind of play with these values, and I hope that gives you a grasp of how hypothesis tests work. So the math behind it is really nothing new. You're basically finding a z-score with your test statistic and computing an area or probability associated with that value to the right of that z-value. Now this is a right tail test. A left tail test would be very similar to this. It would be just a mirror image of what you see, and everything would be conducted in the left tail. And then I have another worksheet set up for a two-tail test, and in that situation you're going to again compute a test statistic, z-naught, but your alpha value will be divided into two red regions, red shaded regions, in the left tail and the right tail. So that's the difference between a two-tail and a one-tail test. So I hope this helps you to understand how hypothesis tests work and the two ways to conduct a hypothesis test. As I said, either comparing the test statistic to the critical value or comparing the p-value to the alpha value. Again, it's a matter of comparing either the location of the z-scores or comparing the shaded area under the normal distribution curve. Thanks for watching.